We will continue our discussion on units and measurements. In the last class, we saw how large astronomical distances are measured using the method of parallax. Now, we go on the other end of the spectrum, that is at the very small range, if we want to measure lengths etcetera, where we need the precision to be less than what we typically find in rulers. For example, if we look at a simple ruler and if we look at the graduation marks in the ruler, the smallest distance which we can measure is 1 millimeter. So, now if there is a line which goes something like this line may fall somewhere, let us say between 101 and 102 millimeters. So, the best we can measure with a ruler will be up to a resolution of 1 millimeter. This is also called the least count of the instrument. So, for a scale with which you measure lengths in class, in drawings etcetera, the least count is 1 millimeter. Now, a 1 millimeter resolution may not be sufficient for our purposes, and we may need measurements which are more precise than 1 millimeter. And for that we have instruments which I am going to explain the working principle of these instruments with which we can measure more precisely. There are 3 such instruments which are typically used. The first of them is called the vernier calipers. In a vernier caliper, this is an instrument which is used to measure lengths more precise than the smallest division marked on the scale. So, how do we do that? In vernier calipers, we introduce a second scale. This scale is also called the auxiliary or vernier scale, and the principle is that typically n divisions of vernier scale are equal to n minus 1 divisions of the main scale. So, now for example, if we have 10 divisions on vernier scale, we will use the symbol V for vernier scale. They will be equal to 9 divisions on main scale. Now, we will use the symbol S for the main scale. So, therefore, one division of vernier scale in this example will be equal to 9 by 10 division of S, which means if the main scale, if main scale resolution is 1 millimeter, then the vernier scale resolution will be 0.9 millimeters. So, let us have a look at this in the form of a figure. So, we have these are the two scales. The bottom scale here, this is the main scale, and the top scale, which is a movable scale, and I will show the instrument to you in a while, is called the vernier scale. Now, as you can see here, 10 divisions on the vernier scale are equal to 9 divisions of the main scale. That means, each of these vernier scale divisions, this is equal to 0.9 millimeters. Having seen this, now let us see how the instrument works. So, here what we have done is, this is the instrument, and what we have done is, we have shifted the vernier scale by a small amount to the right. So, now the 0 of the vernier scale is not matching with the 0 of the main scale. Now, what we will find in typical measurements, this amount which I have shown, the difference between the main scale reading and the 0 of the vernier scale, this is the extra amount which is there after the main scale reading, which has to be read. So, now if you see here, if we count here, the 6th division of vernier, this is matching the main scale reading. Now, because these two scales are unequal, so therefore, since these scales are unequal, one of the readings of the vernier will match the main scale reading. It does not matter what is the number on the main scale, we just have to count the reading on the main scale where the matching takes place. So, now from this figure, it is very obvious that if we want to find this distance AB, then if I look at this total distance AB, and let us see this, AB is what we want to measure, this will be equal to AC minus BC. Now, what is the total distance AC? AC is equal to, we counted, we have 1, 2, 3, 4, 5, 6 divisions of the main scale. So, this is equal to 6 times S, and we look at BC, BC is equal to 6 times V. So, therefore, this length AB is equal to 6S minus 6V. So, from here what we realize is, the minimum measurement which we can take from the vernier will be equivalent to when the first reading of the vernier matches with that of the main scale. So, that will be equal to S minus V, and this is how we get that the, for a typical vernier of the type which I have shown, that the least count of the vernier caliper, which is the smallest distance which the vernier caliper can measure, this will be equal to the main scale resolution minus the vernier scale resolution, if the gap. So, this is the minimum which we can measure. Now, what we have seen earlier was that n divisions of vernier scale are equal to n minus 1 divisions of the main scale. So, therefore, the vernier scale resolution of the vernier scale, not of the caliper, this will be equal to n minus 1 by n times S. So, therefore, the least count of vernier caliper for a caliper where scales are as we have indicated, this will be equal to S minus n minus 1 by n times S, and this will be equal to S by n. So, this is how one calculates the least count of a vernier caliper. Now, let us see how one can take a measurement, and once again, instead of going for a formula based approach, we will look at the readings and try to get the readings and find the length which is to be measured with a caliper using this. Let us assume that in this case the main scale distribution is 1 millimeter. Now, here this is the vernier scale, and what we find is the 0 of the vernier scale, this is the 0, this is coming 0 of vernier occurs after 2 readings of main scale. This is 1, this is 2. So, 0 is occurring after 2 readings of main scale. So, therefore, the main scale reading in this case is equal to 2 millimeters. Now, if we have to measure the length, we have to add this extra distance x to the main scale. Now, to find this extra distance x, what we will do is, let us see, we find this is the reading which is the fourth reading of V coincides. So, here we find that the fourth reading of V coincides with main scale, and it does not matter what is the reading on the main scale, we have to count which reading of V coincides. So, fourth reading of V coincides with main scale. So, in this case, if we look at x, x will be equal to, if we count, we see it is 1, 2, 3, 4 main scale readings minus 4 vernier scale readings. So, this will be equal to 4 into 1 millimeter minus 4 into 0.9. So, this will be equal to 0.4 mm, and so that means the total reading which we will get will be 2 plus 0.4. So, this is the total reading of that length which the vernier caliper is showing to us. So, this is the principle of a vernier caliper. So, let us have a look at an actual vernier caliper. In a vernier caliper, there is a moving jaw which is adjusted, and the object whose size has to be measured is fitted between this is the fixed jaw and there is a moving jaw, the object is held here. Attached to the moving jaw is the vernier scale, and whenever you have to use a vernier caliper, the first thing you should do is to find the least count of the vernier caliper, which means you find how many divisions of the main scale are matching with how many divisions on the vernier scale. Typically, on the vernier scale, the numbers are in some multiple. For example, if we focus on the vernier scale here, what we find is the vernier scale is the one which is at the bottom, and on the vernier scale we have total number of divisions are 50. We have 0 to 10 and each of them is, there are 5 divisions, the number of divisions on the vernier scale are 50 and they match with 49 divisions of the main scale. So, therefore, using this we can find the least count and we can use the method as we have done earlier. And if you do not fall in the trap of blindly using the formula every time, if you work out how much is the distance on the vernier scale, how much is the distance on the main scale, and the difference of these two gives you the extra distance which has to be added to the main scale reading. When we focus on this particular reading, let us see. So, now here we can clearly see that the main scale reading we have 3 centimeters, after that we have to count 1, 2 and 3. That means, the main scale reading is 3.3 centimeters. And then we look at the vernier scale reading. In the vernier scale reading, what we find is the reading which is matching with what is marked as 4 on the lower jaw, 4 is matching with the main scale reading. 4 will correspond to 20 vernier scale readings, because each of them between 0 and 1 there are 5 divisions. That means, the vernier scale reading which is matching with the main scale reading here is the 20th reading. So, here when we have to find the total length which is being measured, it will be 3.3 centimeters which comes from the main scale reading, and in the vernier scale we have the 20th reading which is matching. And if we look at the total vernier scale, we have 50 vernier scale divisions. We are going from 0 up till 50 divisions, 9 into 5 45 plus 5 50 divisions, and they match with 49 divisions of the main scale. So, we can work out the least count, multiply that by 20 and add that to 3.3, that will give us the actual reading. Now, I want to take one more problem where the things have been specified in a non-trivial way. This problem says that there are 2 vernier calipers in which on the main scale 1 centimeter is divided into 10 divisions. So, we have a vernier V1 and a vernier V2, and in both of these the main scale S1 and S2, they will be equal to 1 millimeter. Now, what is given is that in the caliper 1, the 10 equal divisions of vernier are equal to 9 divisions of the main scale. So, this is actually, if you look at it, this is a typical vernier caliper, where 10 divisions of the vernier are equal to 10 minus 1 divisions of the main scale. Now, here the trick comes when we see the specification of the second vernier caliper. In the second caliper, what is given is 10 divisions of vernier are equal to 11 divisions of the main scale S. So, here what we realize is that actually this instrument which we are looking at, the second one, is not a typical vernier caliper, because here if we look at it, each reading of the vernier by itself is equal to 1.1 millimeter, which is more than the main scale reading. Now, given this specification, let us see what the problem says. In the problem, the two calipers which are denoted as C1 and C2 are given, and what is asked is you are supposed to give out the reading, the size as measured by C1 and a size as measured by C2. So, here let us try to first focus on C1. Let us take the reading of the length which C1 takes. So, to get the reading for C1, we look at the main scale. The main scale first is 2.5, then we have 2.6, 2.7, 2.8. So, the main scale reading in C1 is equal to 2.8 centimeters. So, now this is up till where you have measured 2.8. Now, we count, we see 7 divisions. So, after that we have to measure this extra distance x, which is where the last main scale reading was and where the 0 of the vernier is. So, this x has to be added to 2.8, and the amount of x, if we look at it, x will be equal to, now if we count, we see the total number of divisions. So, it is equal to 7 main scale readings minus 7 vernier readings. So, this will be equal to 7 into 1 millimeter minus 7 into 0.9 millimeter. So, this is equal to therefore 7 minus 6.3. So, this is equal to 0.7 millimeter. Now, x has to be added to the main scale reading. So, the total reading by C1 is equal to 2.8 centimeter plus 0.7 millimeter. So, this will be equal to 2.87 centimeters. So, this is how one works out the reading with the caliper 1, and this would have also come in by using the standard formula. Let us now look at the second case. In the second case, what we had was that 10 readings of the vernier were matching 11 readings of the main scale. So, therefore, each of the vernier reading in that case is equal to 1.1 millimeter. Now, when we have a detailed look at the reading, what we find is that on the when we look at the 0 of the vernier scale, before that the main scale reading is 2.8, and if we take the distance from the 2.8, that is the last main scale reading, to 0 of the vernier as x1, then we have to measure x1. And here what we find is, when we look at this figure, the seventh reading of the vernier is matching with that of the main scale. So, if we have to measure x1, x1 is the distance between the main scale reading and 0 of vernier. Now, what we find is seventh reading of the vernier in the figure matches with eighth reading of the main scale, where we take the starting as the last main scale reading. That means, x1 from the figure, if we look at it, is very clear, is equal to 8 main scale readings minus 7 vernier readings. So, therefore, the distance is equal to 8 millimeters minus 7 multiplied by 1.1 millimeter, which is 8 minus 7.7 millimeters, and this we can write it, this is equal to 0.3 millimeters. So, therefore, the total reading which caliper 2 gives us is 2.8 centimeters plus 0.3 millimeters, which is equal to 2.83 centimeters. So, this example clearly illustrates that in an unusual situation you cannot blindly use the formulas, and the unusual situations could be something where you have a different type of vernier scale, or sometimes the divisions, it may not be n minus 1 divisions which match with n, it may be n minus 2 or something like that. Now, I will also leave you with a thought question. Suppose somebody makes a vernier where 10 divisions of the vernier match with 10 divisions of the main scale. Now, you think about it, what will be the least count of such a vernier, or whether if such a vernier will be effective at all or not. I would like you people to think about a vernier where the number of divisions on the vernier scale, if there is an error in manufacturing and they happen to be equal to the same number of divisions on the main scale. What will happen when you take readings with such a vernier caliper? Now, this was one of the devices which I have shown to you. The next two devices about which I want to talk, they are called a screw gauge and another device called spherometer, where the working principle is the same, and this is based on, if we look at a thread of a screw, this has a helical shape, which means, which implies that if we make rotation on the thread of the screw, we also make an axial movement, and this you must have seen, as you tighten a screw it also goes inside. So, therefore, the rotation and the axial movement of a screw are related, and this relation is given by pitch. So, the axial distance moved when we complete one revolution on the screw, this is called the pitch of the screw. So, that means a pitch is a linear length, it is a linear dimension, and this corresponds to a complete revolution, which means a 360 degree rotation on a screw. And so, the principle which is used in these devices is that if the pitch of the screw is known, then it is easy to measure the fractional rotations, because we know a total rotation is equal to 360 degrees. So, and this rotation will be typically on a circle. So, therefore, fractional rotations can be easily measured in degrees and as a fraction of the total rotation. So, that gives us how much is the extra distance which has been moved. So, and this becomes very clear when we show the picture of a spherometer. In a spherometer, this is the, we show the screw which is a screw of the, which is here, and now as we rotate the screw, then the linear scale is there on which we can measure the distance, axial distance which the screw moves, and the partial rotations of the screw are measured by this circular scale. So, therefore, we can measure the full linear rotation, the linear distance moved, and the fraction comes through the circular rotations, and when these two are added, we get the total reading. The other device which is used for this is what we call as the screw gauge. So, in these devices we have the pitch of the screw corresponds to the smallest reading of the main scale. So, what we do is we rotate the spindle by 1 revolution and observe the axial distance which is moved on the main scale. Typically, in instruments like this will be either 0.5 millimeters on 1 or 1 millimeter. So, we keep it in multiples. This is how these screws are manufactured. So, pitch would be something like this. Now, on top of this there is a circular scale or the auxiliary scale, and this enables us to give the fractional reading. So, the fractional reading is taken from the circular scale. So, let number of divisions on circular scale be n, and let pitch of the screw be p. So, here then we can easily observe that least count of the screw or of this device, this will be equal to p divided by n, and the units will be the same units as that of the pitch. Now, if the circular scale reading is equal to m, so then the extra distance or extra length to be added to the main scale reading will be equal to m multiplied by p by n. So, this is a very straightforward way of taking the readings here. We take the main scale reading, and to that we add the least count multiplied by the number of readings on the circular scale, and that gives us the direct reading of the screw gauge. So, of course, the least count for each instrument could be different. For example, in instrument which we have, the pitch may be 0.5 millimeters and number of divisions on the circular scales may be 50. So, in that case, the least count for a screw gauge of this specification will be 0.5 divided by 50, and this will be equal to 0.01 mm. And as we see in typical vernier calipers, if the vernier caliper has 9 divisions equal to 10 divisions, there the least count would have been 0.1 mm, whereas in a device like this the the least count is 0.01 mm. So, as I showed to you, the other device, we showed the figure of a spherometer. Other device which you will be using in your labs is called the micrometer screw gauge. So, here we have a device called the micrometer screw gauge, which you will also be using in your laboratories to measure the diameter, let us say, of circular objects. Now, if we see here, this is the main scale. The pitch of this instrument is 0.5 millimeters. The total range, as it is written here, it measures from 0 to 25 mm diameters. The pitch is half a millimeter, and if you look at the circular scale, then we see it starts from 0 and it goes up to 45 and comes back to 0, which means there are 50 divisions. So, therefore, the least count of this instrument is 0.5 divided by 50, which is 0.01 mm. The object to be measured is put in between these jaws, and this can be rotated to increase this distance, and till the object touches here, we measure, we take the main scale reading, we take the circular reading, circular scale reading, and then we just add up the two as we have discussed. We add to the main scale reading, we take the least count and we multiply it by the reading of the circular scale, and the two are added up together. So, that is how we can make our measurements using a screw gauge. Now, there is one more thing we have to be careful about when we use instruments like this, and that is called the zero error. Zero error is the error which is coming in our reading, and it comes when an instrument, when it is supposed to read 0, it actually does not read 0. So, for example, in a screw gauge or a vernier caliper, when you touch the two jaws, then we should get 0, but there if the reading is, let us say, it is something like 0.05 mm instead of 0. So, which means this is what we refer to as the zero error. So, what is going to happen is, when you actually have 0, the instrument reads 0.05. So, now when you take a reading with such an instrument, then what will happen is, to each of your reading, this extra value is added. So, therefore, the zero error has to be subtracted from the reading. So, each reading which you take from this instrument, you subtract the zero error. Now, note, the zero error can be positive or negative. If the zero error is negative, then you will be subtracting a negative number from the reading, which means you will be adding up. So, this has to be taken care of in all the instruments, whether it is a screw gauge or a caliper. When you take measurements, you start by observing the zero error, and whatever your final answer which you get, you subtract the zero error from the reading, and that is how measurements are. Next, we will talk about accuracy and precision of instruments. These two terms have specific meanings, and we will talk of the errors associated in measurements. Any measurement which we take is not 100% accurate. So, for example, when we measure the length of a line with a ruler, if we measure it as 7.1 centimeters, maybe the actual length of that line is 7.12 centimeters, or it may even be 8 centimeters, but we measure it as 7.1 centimeters. So, when we measure any measurement taken, is not 100% accurate, and the uncertainty or the deviation of the measured value from the actual value. So, deviation from the actual value, this deviation is what we refer to as error. First, let us understand the difference between the terms accuracy and precision. Accuracy tells us how close we are to the actual numerical value. So, for example, if we have to measure something which is 3.8 meters and if we measure 3.5 meters. So, our accuracy, we have missed the actual measurement by about 0.3 meters, whereas precision tells us about the resolution of the quantity which we have measured. So, the resolution or the least count which we have, that gives us the precision. So, for example, if we take measurements from a typical scale, then here the precision would be up to 1 millimeter. So, this is how we define precision. Now, accuracy depends on many factors. And these factors include precision. Let us take an example. Suppose if the true length of a line, this is equal to 3.678 centimeters. Now, we measure this with scale of least count 1 millimeter, and we find this measurement turns out to be 3.5 centimeters. Now, we measure the same thing with an instrument of least count, which is 0.1 mm, and we find the measurement from that instrument is 3.38 centimeters. Then the first instrument which we have with which we have measured is more accurate, because it is closer to the correct value, but it is less precise than the second instrument, because in the second instrument we can measure up till 0.1 mm. Now, the question is, why do these type of errors arise? Because as we have seen, a thing may be more precise, yet it may be less accurate. Now, the type of errors which we find, we classify them into many types. The first type of errors we talk of are systematic errors, and these errors tend to be in only a single direction, that is, they are either positive or negative. And what we mean by this is that if we take 10 measurements from that same instrument and with the same technique, then either in all of them we will be measuring extra, or all of them we will be measuring less. So, they will be in the same direction if they are systematic errors. Now, the systematic errors, there can be many causes of this. The first cause could be because of the instrument. It could be an instrumental error, and here this could be because the calibration of the instrument is not perfect. So, and this is what zero errors, which we discussed a bit earlier, are basically because of this type of a case, that for example, in a vernier caliper, 0 of the vernier may not coincide with 0 of the main scale, and so whatever if it is occurring in a, if we get a positive value of the vernier, that means what we are getting, we are adding that extra amount to all the readings. Now, the other systematic errors. So, in addition to the instrumental error, we could also be, there could be error due to experimental technique. For same quantity, you could be measuring it using different ways and there may be errors. One typical example of this is when we measure temperature of the human body. So, we can either measure, we can keep the thermometer under tongue or under armpit, and these two different techniques of measurement in the same person will give, even if we take the readings at the same time, they will give different temperatures, because it is known that temperature under the armpit is lower than temperature under the tongue. So, therefore, if two different techniques are used to measure the same quantity, there could be an error because the two techniques are different. Then the third type of error which come under the systematic errors are personal errors, and these errors could come because of individual bias, because of the setting of the instrument, or because of carelessness of the observer. Now, sometimes, for example, if you are looking at a scale and if the scale is vertical, if you look at the scale from the top or if you look at the scale from the bottom, you will observe different readings, and these are sometimes also called as errors of parallax. Another same thing you may have observed if you are looking at the speedometer of a car, which is also called the odometer, and if you look at it from the rear seat, a person who observes the speedometer from the left side, left seat, rear seat, or the right rear seat, these two people for the same reading will observe different readings, and such errors are what we call as personal errors. Now, in addition to this systematic errors, there is a second type of errors which we call as a random error. Random error, they occur irregularly and they are random in nature, which means this could be because of unpredictable fluctuations in the instrument. There could be fluctuations in temperature or in the conditions. So, there could be fluctuations in temperature, fluctuations in voltage, or we could have vibrations of the in the setup. All these lead to random errors, and random errors typically would be in both directions. They could be either positive or negative. For the same, when you are taking the same reading of the same quantity again and again, they would be in both directions. Then there is one more error which we have already seen, and this is called the least count error, and this has to do with the smallest resolution of the instrument. So, for example, if we look at a vernier caliper, what is the least count of a vernier caliper? Now, if you answer 0.1 mm, well, that will not be a correct answer. For me to be able to know the least count, I have to know what is the vernier scale, what is the main scale division, and unless I know this, I can't answer what is the least count of a vernier caliper. But suppose you measure the least count of a vernier caliper, and if least count of caliper is observed to be is equal to 0.1 millimeter, then that would be the least count of error related to the vernier. So, you can't answer questions like least count of an instrument without knowing the details of that instrument. Now, when in some cases when we take measurements and we want to find out the associated error, then we are using the same instrument to measure the same quantity. Then how will we figure out what is the actual or the accurate reading for that value? And it may not be possible for us to know the precise reading. In that case, what we do is we repeat the observations. So, when we take measurements, but we do not know what is the actual value of this, we repeat the observations, and then what we do is we take the arithmetic mean of these readings, and this arithmetic mean is what we take as the actual value. So, the mean is taken as the actual value. So, we repeat observations and then we take the mean as the actual value. So, associated with this we have three terms: absolute error, relative error, and percentage error. So, we describe each of them one by one. So, first suppose we take, let us take n measurements, and these measurements we denote by A1, A2 up to An. Now, the mean of these is given by A1 plus A2 plus An by n, and we also can put it in terms of a sigma notation, which we say take sum of I going from 1 to n, A sub I, this is the summation, divided by n. So, this is what we take as the mean, and now the magnitude, this is, so this is very simple calculation of the mean. Then what we do is we calculate the magnitude of the difference between individual measurement and the true measurement. And in this case, the true measurement, in the absence, if we do not know this, will be taken as the mean, and this, if we take the absolute value of this, we call it as the absolute error delta A. So, this will be equal to, this is how we calculate the absolute error corresponding to each of these in each of the readings. So, this will be equal to the ith reading minus the mean, and we take the absolute value. That means, in whichever direction the error is, we take its absolute value. So, let us have a look at this for the case where we have n measurements A1 to An, the true value not known. So, we will assume, so mean is taken as the true value. So, a mean, as we have discussed before, is equal to A1 plus A2 plus An divided by n. Now, the error in the first reading A1, this will be equal to A1 minus A mean, error in the second one is equal to A2 minus A mean, and so on. Then we have the nth reading, this will be equal to An minus A mean. Now, what we do is, this delta A can be positive or negative. Each of these can be positive or negative, but we take their absolute values. So, therefore, absolute value of delta A, this is always positive. Next, what we do is, we take the arithmetic mean of all absolute errors, and this is called the mean absolute error of A. So, delta A mean is equal to magnitude of delta A1 plus magnitude of delta A2 plus magnitude of delta An divided by n. So, now what we will say is, if we look at any single measurement, we expect this to be in the range A mean plus minus delta A mean. That means, each measurement which we take will be, the A mean gives us the value of the measurement, the true value, and the error which we can expect will be the absolute mean absolute error, and it could go in either direction. So, A mean plus minus delta A mean is what we expect. That means, all measurements which we take, they will be in the range A mean minus delta A mean. This will be less than or equal to the measurement which we take, and the maximum value of this could be A mean plus the absolute value. So, this is how we expect the our errors, our measurements to lie in this range. Finally, we define the third term, which is called the relative or percentage error. There are two different terms, and we will talk of them. And in relative error, what we see is the relative error is given as the absolute error in the measurement divided by mean. So, relative error is always a fraction, and generally if measurements are reasonably accurate, this fraction should be less than 1, because you do not expect the error to be of the same size as the mean that would be. So, relative error is normally a fraction, and it gives us the relative order of error as compared to the true value, and we express this as a percentage. Then we call this as a percentage error. The symbol often used is small delta, the Greek symbol A, and this is the relative error expressed as a percent, which means we will multiply it by 100, and then we will call it as a percentage error. Now, let us have a look at an example here. Suppose we are measuring time period of oscillations. So, here we take 5 measurements, and these measurements are 2.63 seconds, 2.56 seconds, 2.42 seconds, 2.71 seconds, 2.80 seconds. That means, these are the same quantity is being measured in 5 different realizations. Each experiment which we do is also called a realization. So, we are doing the same experiment 5 times and we observe the time period of oscillations are given by this. Now, you realize in each of these the accuracy of the precision of the measurements is up to the same order. That means, we are going up till 0.01 seconds. Now, if I take the mean of these, to calculate the mean, I will first have to calculate the sum and divide it by the number which is equal to 5. When I sum it up, this summation value comes out to be 13.12 seconds, and so the mean will be equal to 13.12 divided by 5, and this turns out to be equal to 2.624 seconds. But we should now be careful. Our number which we are getting here is 2.624 seconds, whereas our measurements were correct up till 0.01 seconds. So, that means, when we express the mean, we will put it as 2.62 seconds, not 2.624 seconds. So, the mean is always written in terms of accuracy up till the same accuracy as the, in terms of rather precision, as the same as the original readings. So, the third decimal here is removed and we round it up as 2.62. Now, we calculate the absolute errors here. To calculate the absolute errors, we once again look at this. So, we calculate delta A1, delta A2, delta A3 in the same example, A4, delta A5. So, this will be now the mean value which we shown was 2.62, the mean value is 2.62, the first reading is 2.63, 2.56. So, from each of these we will subtract 2.62. So, delta A1 is 2.63 minus 2.62, this is equal to 0.01, delta A2 is 2.56 minus 2.62. At this stage, let us put the sign also, but when we find the absolute error, we will take the absolute value. Delta A3 is 2.43 minus 2.62. So, this is equal to minus 0.20, and all of them have the same units as the original one, which is seconds. Delta A4 was 2.71 minus 2.62. So, this was equal to 0.09 seconds, and the final one is 2.80 minus 2.62. This is equal to 0.18 seconds. So, here if we now calculate the absolute error, we will add up all these, but we will add up the absolute values. So, this will be equal to 0.01 plus 0.06 plus 0.20 plus 0.09 plus 0.18. We add up all these and we divide by 5. So, if we calculate this, the absolute error turns out to be 0.54 divided by 5, and once again the final answer we will write up till 2 decimal places. So, this we will write it as 0.11 seconds. And so, if this is the error, then what we will say is the time period is equal to 2.62 seconds, which was the mean, plus minus the absolute error, which is 0.11 seconds. Now, here we also observe one more thing, that the error itself is greater than 0.1 second. the error is plus minus 0.11. So, because it is greater than 0.1 second, so what we will do is we will write the time period as 2.6 plus minus 0.1 second, because there is no point going up till the second decimal place when the error itself is 0.11 seconds. So, this is how we express the final answer. And if we want to calculate the relative error here as a percentage, relative error will be 0.1 divided by 2.6 into 100, and this will be equal to 4%. So, this is how we calculate the errors, and you may have noticed that we have gone up till a particular number of digits here. How many digits do we consider will become more clear in the next class, where we will talk of significant digits. We will take that up in the next class.